CS1010X Lecture 4 Recursion, Iteration, and Order of Growth. Here's a quick review. Lecture 1, you got to know about Python. Lecture 2, you got to use Python for single function abstractions. Lecture 3, we started to have some strategy on solving problems. Now, in Lecture 4, we are going to look at recursion versus iterations ways of solving problems and how good is your solutions. We touched on this in Lecture 3, and in this lecture, we're going to go into the detail about the time and space complexity. In this first of the 3 parts video, we revisit recursion again. In recursion, we know about base case recursion of smaller problems. Near the end of this video, you will see an example where we can use recursion to carry baggage along with it. A recursion solution has 2 parts, the base case or base cases and smaller problem or problems. Recursion is a form of wishful thinking where smaller problems have the same structure as the original problem. The examples we saw in the last videos are the factorial, which is a linear recursion, and Fibonacci numbers, which is an exponential recursion. In this video, you're going to see a few more examples. Example 3, Greatest Common Divisor. That is, given 2 integers a and b, what is the largest number that can divide both a and b? Now let's see the Euclid's algorithm on solving this problem. The input is a and b with a larger than b. If b is larger than a, you can figure out that the algorithm works too. The Euclid's algorithm says that the GCD of a comma 0, that is b equal to 0, is exactly a, because a is the largest common divisor of a and 0. That means a can divide a and a can divide 0. If not, GCD of a comma b, where b is non-zero, then the answer is the same as GCD of b comma r, where r is actually the remainder of a divided by b. You can see that b is smaller than a, so this b is smaller than a, and the remainder is smaller than b. So as a result, these 2 parameters are smaller than the original 2 parameters. So the problem of GCD AB is now converted to a problem of GCD BR, which has the input smaller than the original input. So this is a smaller problem of the original, and so these form the recursive structure. Let's see an example. GCD of 206 and 40, so A is 206, B is 40, is the same as GCD of 40, 6, because B is 40, 6 is the remainder of 206 divided by 40. So 40, 6 is the same as GCD 6, 4. Why? 6 is the B and 4 is the remainder of 40 divided by 6. So you get the remainder 4. The GCD of 6, 4 is GCD of 4, 2. So the B is here and the remainder of 6 divided by 4 is now the R. You continue, you have 4, 2. 2 is the B, so B is here. 4 is divisible by 2, so you get a 0 as the remainder. So in this case, A is 2 and B is 0. So the GCD of this by the base case is 2. Now, these 2 statements are easily converted to our Python code. Define GCD A, B. When B equals 0, if B equals 0, we return A. Otherwise, GCD of AB is the same as GCD of B, R. Return GCD B, A divided by B to get the remainder. This completes the program. Example 4, Towers of Hanoi. This is yet another classical example that can be solved with recursive algorithm. You're given 3 pack A, B, C with A containing 3 disks here. It can be n number of disks in general. For here, we just use 3 for illustration. Your job is to move this stack of disks from A to C. The rule is that in the movement, there is never a bigger disk on top of a small disk at all times. That is, you always see from bottom to the top, it's always bigger disk to smaller disk. And it is understood that you can move only 1 disk at a time. Now, why is this recursion? Right, if you ignore the largest disk at the bottom, then you would have n-1, in this case 2 disks. Your job is to move 2 disks obeying the rule. So this is a smaller problem when you ignore the largest disk at the bottom. Right? Since your goal is to move from A to C, you can think of it as first moving the n-1 disks from A to B without violating the rules at all time, then you move the largest at the bottom directly to C. Next, since you have 2 already here, or in general n-1, you can then move this from B to C. And we are now done with the requirement to move all disks from A to C. The discussion so far tells us how to solve the problem with 2 calls to smaller problems of size n-1. Let's see the code. Define move tower size from A to C with B as the intermediary. If the size is 0, this is the base case, meaning that there's nothing to do and we return just true. Otherwise, we have to do the work. First, we move the n-1 disk from A to B using C as the intermediary. As to how this is done while obeying the rule and moving disks one at a time, we leave it to the recursion. With this statement completed, we see that C is still empty and A is left with only the largest disk. So we can then move the disk from A to C. And this leaves A to be empty. The smaller problem is then to move this n-1 disks from B to C. So we have move from B to C using A as the intermediary. Again, as to how this is moved, we leave it to the recursion and we are done. When you run this code with move tower 3 disks from A to C with B as the intermediary, then you get these lines of outputs. First you have from A to C, which is the smaller disk got moved to the C. Then you have from A to B, which is the medium guy, get moved to B. And then you have C to B, which is the smaller guy, back to B. And you have from A to C, which is the big guy, go to C, and so on. And this is what you wanted. And along the way, you see that it obeys the rule that there's no bigger disk on top of smaller disk. Right? Like here, these are medium to small, medium to small. Here, large to medium. So this routine is correct. Example 5. We are given 50 cent, 20 cent, 10 cent, 5 cent, and 1 cent coins. Our task is to find change for $1. So it could be 2 50 cents to change for $1, or 1 50 cent, 2 20 cents, and 1 10 cent, or 5 20 cents, etc. So assume we have unlimited number of coins available, meaning that we can use as many as we want for each type of the coins. Now the question is, how many ways to change for $1? Alright, so here are 3 ways, and then in fact there are hundreds of ways to do this. We want to find out what is the number. So why recursion? Well, recursion meaning that we have to think about smaller problems. Can we divide it into smaller groups to count? Yes, here's one way to think about it. A group that uses at least 1 50 cents plus another group that uses no 50 cents. So these two together give us the total number of counts. For counting, it's very important that we have to ascertain, are we undercounting, meaning that we miss out some of them? Are we overcounting, meaning that we counted someone more than once? So for undercounting, do we count every single one? Yes, every single one is accounted for. Every single one is either using no 50 cent or using at least 1 50 cent. Are we overcounting? No, because every single one is in one of the 2 groups and not both. Alright, so if you use 50 cents, you are in here. If you don't use 50 cents, you are in here. So you are not counted twice. So we now know that this is a correct divisions of the problem into 2 problems. Then why are these 2 really smaller groups, smaller problems? Because the count here is going to be a number smaller than the original problem, and the count here is going to be a number smaller than the original problem too. So we now know the problem has recursive structures, but we are still missing the base cases. So what are the base cases? These should be cases that you can easily count them, given the amount A that you want to change and the number of types N of coins you have. Because here, with 50 cents, you would have 5 types. Without 50 cents, you now have 4 types only. So when the amount is 0, that means there's only one way to change it, regardless of the number of types of coins you have. That is, you don't use any coins. To get a negative amount, there's no way that you can use any coins. or no coins to change it. So the number of ways is 0. If you have no types of coins, n equal to 0, then again, regardless of the amount, there's no way that you can change it. So the number of ways is 0 also. Now we write the number of ways to change the coin for amount A with number of types of coins n equal to this plus this. So for this base case, A equal to 0, the number of ways is 1. This is written as CC0, n equal to 1. And for this case, n equal to 0, CC equal to 0 also, we have CC A, 0 equal to 0. Now what about this one? This one is with at least 1 50 cent. So the amount A must be subtracted away with the 50 cents. And the number of types of coin remains as n because we can continue using n number of types of coins. So it's CCA minus 50, n. What about this one? This one is those that do not use 50 cents. So the amount A remains the same and number of types of coin n would have to minus away by 1 to get rid of the 50 cents. So CC A, n minus 1. So these are the base cases with the formula, and this is the recursive structures to calculate CC A, n. We are now ready to code up this counting change. So we have the base case and we have the recursion formula. So it is kind of straightforward. So you define CC A, n, the amount and number of types of coins. There are 3 base cases here. So if A is equal to 0, you return 1. Alright, so this is the first case. Else if A less than 0, you return 0. This is the second base case. Else if n is equal to 0, return 0 also. This is the last base case. Otherwise, we have to go into the recursion, which is CCA n equal to this plus this. Else return CCA minus 50, n plus CCA, n minus 1. Now you notice this 50 is actually because we have 5 types of coins, so the denomination is 50. But when this number of types of coin goes down, this has to change according to the n, the number of types of coins we have. So this should be another function. We call it denomination depending on n. Then we have to code out the denomination. So define denomination n. If n is 5, number of types of coin is 5, we return 50. Else if n equal to 4, we return 20. Else if n equal to 3, we return 10. Else if n equal to 2, we return 5. Else if n equal to 1, this is the last coin, and that is 1 cent coin. Else they return 0. With number of types of coins is 0. Let's check it out whether this is okay. We can try out print CC 100 $1 with 5 types of coin. We would expect 343. The number of ways to change this. 343. So this is correct. Now, a few things that we can check it out. A equal to 0, that means the amount equal to 0, return 1. When the amount is less than 0, you return 0. And let's say if you ignore this, and what happened? Let's run. You'll see this recursion never ends. Because indeed, at this A minus denomination, this can go below 0 when the recursive call. So this is the needed base case. What about this one? This is the number of types is equal to 0, you return 0. Let's say if you comment out this also, what happened? Again, we are in trouble because we have exceeded the recursion depth. Why? N indeed can be equal to 0 when this n minus 1 keep going into the recursions, and at some point n will become 0. We will continue to go inside here and this thing will never end. And therefore, all these 3 base cases are needed and without fail. Now, what about this routine? This routine looks ugly. Instead, actually, you will learn this. You could have make this as denominations equal to a tuple as 1, 5, 10, 20, 50. Then it is easy to write this function as return the norm, that particular one. When n is 5, we will want to return 50. So 0, 1, 2, 3, 4. So this will be n minus 1. So these three statements can replace this whole chunk of conditional. Okay, let's try it out. Or if you want, you can comment out this. Format, comment out. Then we run this. The tuple object is not callable. So this is the wrong way to say the tuple object. We should put a square bracket to indicate that this is that particular item instead of a parenthesis. Run. Now we are okay. So you can also try denomination 5. It's indeed 50. Denomination 1 is indeed 1. Alright, so these two lines can replace this whole chunk. Alright, so we have what we wanted. This is counting change. We next see counting change in another way to help us understand carrying baggage into recursion. This is yet another useful task that recursion can do. The problem we want to solve is to list out the actual ways to do the change. For example, there are 9 ways to change 20 cents. We can use 2 10 cents or 1 10 cent and 2 5 cents, etc. So we want to have this routine cc_listing to list out the actual ways to change 20 cents with 3 types of coin. They are 5 cent, 10 cent and 1 cent. And this extra parameter here is the answer we need to carry into the recursion. So how do we do this? Let's go to the idle. The first thing we do is to copy this routine, the original routine, and put it there. And we want to do cc listing 23 and the answer. And so this is cc. We need to change this to cc listing, and cc listing. Okay, so this is the original. And we say that cc listing has a third parameter. So this is the answer that we need to carry into the recursion. So this is a partial answer. Currently, when we call, the partial answer is empty. Now, looking at this structure, you see that when a equals to 0, you return 1. So at this moment in time, you indeed have found solutions. So this is the place where you can print out the solutions that you have. So we print the solutions. Next, a less than 0, you return 0, so there's no solution here. N equal to 0, return 0, so there's no solution here. So how does this got accumulated? You see that there are two parts here, cc listing. A, taking away the denomination, for example, the 50. So at this moment, you know that you use up this particular denomination. So it must be the case then that this partial answer must be augmented with this denomination then. Alright, but because this denomination is a number, we need to change it to a string. So we put a string around it. And you see that our solution is such that it's 10 plus something, 10 plus something. So we have another character for it. And that's it for this recursion. Now, as for this recursion maintain the amount and just use one less type of coin. So as it is, there is no new coin added to this solution. So the partial solution remains the same as the partial solution. That is, this answer so far is the same as the original answer. Okay, so that's it. We are done with these corrections needed to the CC to change it to CC_listing. Let's try it. Oh, this 343 is from this print statement. So we don't have to worry about that. So this CC listing gives us this. Now the answer is close. We just have to get rid of this extra plus because of this plus here. And before we print out, we can then just ignore the very last character. So this is how we can ignore the very last character. And let's try this again. Here we have the same as what we needed to find. So 10, 10. And of course, if you want to print out the 9, so let's try. Put the print around this and let's run again. Yes, we now have the 9, the number of ways. And besides this, we have the listing of the actual ways to do the change. And we are done. To sum up this video, we have seen recursion again for base cases and recursively into smaller problems, Plus, we have this baggage to carry along, that a task that recursion can help. For recursions, we have seen the two examples, factorial and Fibonacci, in the previous video. And this video, we have seen the GCD, which is a special kind of linear recursion that called tail recursion. Then we see example 4 and 5. Both are exponential recursion. In counting chain, we illustrate how to carry baggage into recursion. For counting, bear in mind, for your future reference, there should be no overcounting and no undercounting to get the correct count.